We introduce TripOptimizer for generative 3D shape optimization and drag prediction using triplane variational autoencoder networks. Current aerodynamic shape optimization is limited by computational and geometric constraints. Watertight manifold geometry is required. Even small styling changes must be repaired and remeshed, often for hours. At every step, primal and adjoint CFD solvers must be converged in HPC, with hours to days typically required. Design parameters cannot be transferred from one design to another. Therefore, a new parameterization must be rebuilt. Without a fast circuit, feedback is slow and trade-offs cannot be explored in real time. Given an input mesh, we sample point clouds on the car surface. This is given to an encoder that maps this high-dimensional input to a low-dimensional latent space. TripOptimizer uses two additional heads, a decoder that reconstructs geometry via semi-continuous occupancy fields, and a predictor that estimates the drag coefficient CD. For a given targeted drag, the gradients are backpropagated and the encoder layers are fine-tuned to obtain an optimized latent vector that is decoded later to the final new geometry. Our model is trained on the DrivAerNet++ dataset, a large-scale, high-fidelity automotive aerodynamics dataset with more than 8,000 industry standard designs. DrivAerNet++ spans all conventional car categories: fastbacks, notchbacks, and estate backs. It also covers EV styles as well as internal combustion engine variants, enabling category-robust learning. To test the performance beyond the training set, an out-of-distribution study was carried out on a salient geometry that was not used for training or validation. Two regions, the roofline and the rear bumper, were morphed by 8 cm along the local surface normal, producing four variants. The base and morphed shapes were then evaluated by TripOptimizer and independently by high-fidelity CFD to determine whether the aerodynamic effects of local edits were predicted accurately. The direction of change is predicted correctly and the magnitude is closely matched to CFD, about 1% error in the most impactful case and 0 in two others. We show two case studies using the same train model, an electric SUV and an internal combustion engine sedan, starting from baselines with targeted aerodynamic drag reduction of 10%. TripOptimizer was able to optimize both designs while having high-quality geometry reconstruction and preserving the design intent. In order to validate our approach, we run independent high-fidelity CFD with more than 150 million cells and evaluate the optimized shapes against their baselines. Here, the optimized geometry shows less flow separation. In addition, the wake region behind the car is more structured and less chaotic compared to the baseline, indicating reduced pressure drag and better control of the rear wake. This led to a 9.6% aerodynamic drag reduction. For the sedan model, the optimized geometry eliminates the flow separation observed on the hood, resulting in improved flow attachment and reduced total pressure loss in the front region. The optimized design also shows a visibly reduced wake behind the side mirror and the front wheels. The wake behind the car is smaller, leading to an 11.8% reduction in the aerodynamic drag. Finally, we analyzed the latent space with TS&E, where clustering is found to follow geometric similarity rather than discrete labels. Points colored by drag values show a clear performance gradient. Low drag designs concentrate in one region and transition smoothly to higher drag areas. One cluster can be seen for the designs with smooth underbody relevant for AVs and another for the internal combustion engine cars with detailed underbody. This structure indicates a physically meaningful embedding that can be exploited for targeted drag reduction. We hope TripOptimizer encourages more work on fast, reusable surrogate-based area design and that it becomes a practical tool for design optimization, giving real-time guidance. Thanks for watching.